Hello again. In this video, we are going to discuss the basis vector representation of a symmetry operation in a point or space group. Recall that a representation of a group is a set of 3 by 3 matrices that follow the same multiplication rules as do the elements of the group. Let us begin with the natural basis for the space R3. The basis vectors are I, 1, 0, 0, J, 0, 1, 0, and K, 0, 0, 1, where I, J, and K are vectors. I've left off the arrow at the top for clarity later on, but we're to interpret those as the basis vectors for R3, specifically the natural basis. Now let us imagine that the symmetry operation, which we're going to denote by the capital letter R as in rotation, has the effect when it acts on the basis vector I, it transforms it into I prime. It also changes the natural basis vector J into J prime and converts the basis vector K into K prime. If that is true, then we can write down R by a new basis vector representation, I prime, J prime, K prime, where each of these differently colored terms here are actually a column. So this is a column of 3 entries. This is a column of 3 entries. This is a column of 3 entries. So we have here a 3 by 3 matrix representation of the symmetry operation R. You might already be quite familiar with how to write out a 3 by 3 matrix representation for a rotation using the sines and cosines of the turning angle, which you probably have seen before. So this is another way to come up with a representation, which often has a number of advantages. The first advantage we'll see is that you can often write down the representation right off the top of your head with little or no calculation. The second we're going to go into even further is the fact that if we have a series of rotations, we can multiply the rotations, effectively multiply a series of 3 by 3 matrices in a very simple way to quickly determine the effect of a combination of symmetry operations. We start off with the simplest possible example, where our symmetry operation is simply the identity E. And we recall that the effect of the identity is to transform the basis vector I into I, the basis vector J into J, and the basis vector K into K, because it is the identity. So from that, we can write down a representation of it in terms of this type of a concept. So the effect on I is to turn it into I. So I prime here is just what was I before. The effect upon J is to turn it into J prime, but it's just J because it's the identity. And then finally, the effect on K is to transform it into K prime, which is, for the identity, is just the same as K. So we get that our representation is simply I, J, K. If we write out this matrix explicitly, we have the I is the 1, 0, 0 column. So each of these is a column vector. The J is the 0, 1, 0 column. And the K is the 0, 0, 1, where we've color-coded the numbers in the 3 by 3 matrix to show to which term in this row matrix they conform. Now this may be such a trivial example, it's not clear what we're doing, so let's try a more complicated case. So now let's try a more complicated symmetry operation. A C4 about the z-axis. So this is a 90-degree counterclockwise rotation. So let's look at the effect upon the basis vectors I, j, and then k would be perpendicular to the whiteboard. Well, if we do a 90-degree rotation, that takes the I vector into the j vector. It takes the j vector into the negative I vector, and the k vector is unaffected. So we can immediately write down the matrix representation of this in terms of what happens to the basis vectors. So recall, I goes to I prime here, so I goes to j, so our I prime here is actually just the vector j. So that's the first term we write down. Similarly, r affects j to turn it into j prime. Well, our 90-degree rotation takes the j vector and turns it into the minus I vector. And we refer to the minus I as I with a hat over top of it. That's the equivalent of minus I. And the k vector is not affected at all, so we just leave that as k. So this means that our representation for the C4Z rotation is j minus I k, where this is to be interpreted as a 3×3 vector. Writing the matrix out explicitly, we have 0, 1, 0. So this is the first column, which is j. The second column is minus I, so we have minus 1, 0, 0, compared to ordinary I. And then our final column is k, 0, 0, 1. And for your own work at home, verify that this is exactly the same form that you would have if you had worked out using sines and cosines the rotation matrix for a 90-degree counterclockwise rotation. And notice how quickly we were able to derive the form without having to know anything about sines or cosines. For our next example, now let's look for a C2 about the z-axis. So this is a 180-degree rotation. And we notice that I gets transformed into minus I, j gets transformed into minus j, and k is left unaffected. Therefore, since I goes to minus I, our first column vector is going to be the minus I vector. We know that j gets transformed into minus j, so our second column is going to be the minus j vector. And since it's rotating around the z-axis, the k vector is unaffected, so it just stays as k. And see how quickly we're able to write down a representation for that rotation, just based upon the effect upon the way that the symmetry operation affects each of the natural basis vectors independently. And now we can write it down as a 3×3. We have minus I, so that's minus 1, 0, 0. The second column in green is the minus j, so that's 0, minus 1, 0. And k is unaffected. That is our third column, so that remains as 0, 0, 1. Again, I refer you to the standard method for constructing a rotation matrix and see how we were able to do it with a great savings in labor over the traditional way. We're going to see for the next example a way of generating a basis, a representation that is very, very much easier than we would get, and we actually get a slightly different matrix than we would using the standard method. Now we're going to look at a much more complicated rotation. So here is going to be a C3 rotation, and the rotational axis is going to be a line that where x is equal to y is equal to z, So the effect is very difficult to draw on this particular sketch to give us a three-dimensional effect, but we want to have a standard right-handed coordinate system with I, J, and then K is perpendicular to I and J. Let's kind of give a three-dimensional effect here. And if we have the rotational axis is the axis that comes diagonally so that x is equal to y is equal to z, the effect of the C3 rotation would be to take I to J, J to K, and then K back to I. So it's difficult to kind of visualize what's going on there, but we're taking a very specific C3 rotation. So notice I goes to J, so our first term is going to be J. The rotation takes J to K, so our second term is now going to be a K. And last but not least, the rotation takes K to the vector I. So our third and final column is going to be the I vector. So this gives our representation, JKI, as this following 3 by 3 matrix. One thing to note is that compared to the matrix that you would develop, if you have a C3 rotation purely around the z-axis, you would have along the diagonal a minus a half, 1, and then you would have off-diagonal terms that involved square root of 3 over 2. And this is a difficult matrix for students to develop on their own, because to develop it, one generally needs to use a certain amount of trigonometry and a little sketch of an equilateral triangle. However, we could write this down without knowing any trigonometry at all, and know nothing about sines and cosines. Now, this particular matrix looks different than the one that you might have developed otherwise, but it shares an important commonality with the other matrix. Here we notice that if we add up the entries along the diagonal, the trace here is 0. In the matrix with which you may be more familiar, it's minus a half, plus 1. Again, the trace is 0. One thing that we know is that for a symmetry operation, if we take a similarity transformation, the trace stays exactly the same. So if all we need for a particular application is the trace of the matrix, then we can devise and construct this matrix very much more easily than the standard rotation about the z-axis. One large advantage of using the basis vector representations for symmetry operations is that if we multiply two of these representations with each other, we have a nice shortcut which we call the multiplication law. Let us assume that we have a 3 by 3 matrix here, where each A, B, and C is each a column, as we've been doing so far, and that I is a column vector 1, 0, 0, for example. Then if I multiply this matrix by this matrix, I simply get A. If I multiply the same matrix times J, the result is going to be B, and this particular matrix times K, I get equal to C. This is just a special case of the fact that we can think of a multiplication of a matrix times a vector as giving a linear combination of the columns. That's one way to think about it. But the advantage of this type of a multiplication system is that we can make another interpretation. So I have this particular matrix ABC here, which is really a 3 by 3 matrix. When it multiplies by I, multiplication by I means pick whatever the first term is and then write it down. So this I here I can just interpret as the first column. Just pick it. That's the answer. When I have this multiplication by J, I can interpret multiplication by J as just pick whatever the second entry is and write it down. So this is, look at the second thing. It turns out this is orange B. Similarly, if I multiply by K, my interpretation is just take whatever the third entry is and write it down without any change. We will see shortly more detailed examinations of how we can use this exact multiplication law to very quickly and easily multiply a series of 3 by 3 matrices. We have already worked out that a representation for the operation C2 around the z-axis is minus I minus j k. Now we're going to use the multiplication law to see the effect of two such C2 operations in a row. Effectively, we're multiplying C2z times C2z. When we use this particular shortcut for entire 3 by 3 matrices, we multiply from the right. So here we have minus I. So we're simply I would be just take the first term, but since it's minus I, it means we take the first term and then flip the sign, so that turns this minus I into I. Similarly, for the second term, this means take whatever the second term is over here. If this was just j, it would mean take whatever the second term over here was, which would be minus j. But since we have a minus sign on it, it means we take the sign here and flip it, so that converts our minus j to j. And then last but not least, we have that this k here means take whatever the third term is in the third column and write it down directly as it is, and we see that it's simply k. So therefore, the product of these two 3 by 3 matrices is simply ijk, which we know is the identity. Which isn't a surprise, but it's a verification that our application of the multiplication law was correct. So let's try to look at a somewhat more complicated example next. Recall that our representation for the C4 rotation around the z-axis was j minus ik. So now we want to see the effect of two consecutive C4 rotations around the z-axis using the multiplication law to simplify the calculation. So more explicitly, this multiplication is j minus ik times j minus ik. Recall that we do the multiplication from the right. So this j here tells us take whatever the second term is and leave it exactly the way it is. So our second term here is the minus I. So minus I goes right there. This term here, if it were an I, would be just take the first term over here without any change. But since it's a minus I, it means we take this term and flip the sign. So that's going to be minus j. Finally, this k here tells us take whatever the third term is in the first matrix and write it down without any change. So that stays as k. And the product, therefore, is minus I minus jk, which is exactly the C2z rotation. So that checks out perfectly that gives the correct result. Now we will try to do a series of rotations that are out of the xy plane. Recall that we have the representation for the C3 around the line x equals y equals z as jki. And let's see what happens if we do two consecutive C3 rotations around that axis. So this series of rotations is jki times jki. We remember that we do the multiplication law from the right hand side. So our first multiplication is j. J simply means take the second term, the second column from this particular matrix, which happens to be k, so our first entry is going to be a k. Next, we have a k here. K means take whatever the third entry is, the third column, and then write it down in this particular place. So that gives us the I vector there. And then finally, the I at the end says take whatever the first column here is and write it down exactly as it is. And the first column here is a j, so we write down a j. So this gives us that the result of this multiplication is a 3 by 3 matrix Kij. if we write this down explicitly, the k vector is 0, 0, 1, I is the column 1, 0, 0, and j is the 0, 1, 0. So we see this since we're multiplying C3 times C3, this is our expression for C3 squared. But we also recall from the nature of C3 rotations that if I do 2 consecutive C3 rotations counterclockwise, that is equivalent to a C3 rotation clockwise. So therefore C3 squared is equivalent to C3 to the minus 1. And I leave it to you to verify that this is exactly the representation for a C3 rotation in the clockwise direction. That is equivalent to C3 to the minus 1. For our final demonstration of this method, let's show that the expression that we had just derived for C3 squared, this Kij, which I told you was the inverse, the C3 to the minus 1, let's prove that it actually is the inverse of C3 xyz by direct computation. So we write down the matrices explicitly, at least in this shorthand form. So C3 xyz is jki. C3 to the minus 1 is kij. So let's use the multiplication law. Remember, we multiply from the right. So our first term is k. K means take whatever the third term is here and write it down directly. So that's the I vector. The second column is an I. That means take whatever is the first term here and write that down as the second column here. So that is the j. And the final term we get by this j here means take whatever the second term is over here and write that down directly, and it turns out that's a k. So the result of C3 times C3 minus 1 is the vector ijk, which is precisely the identity. Therefore, we proved that this vector, which we assumed was the inverse of C3, actually is so. I thank you very much for your attention. As always, have a good one.